Oops, before I forget it, there's another important difference compared to the wind-driven circulation in the Pacific. Have a look at the structure. One important difference is in the Atlantic Ocean, there's actually a significant flow crossing the equator on the western side. You can see it here. Okay, it starts with the equatorial current, North Brazil current, and goes across the equator, and this actually feeds into the Gulf Stream. And this flow across the equator is actually facilitated because at depth you have a deep western boundary current that moves water across the equator in the opposite. Okay, so these are coupled processes here, and this return flow near the surface across the equator is the return flow of the deep circulation. Okay, but what I wanted to talk about is now other aspects of the equatorial. And just very, very quickly, just a little sketch here. Near the equator, the circulation in all oceans is generally dominated by zonal currents, currents from east to west or west to east. Very, apart from what I just said before, very dominant features along the equator. And this is because the Coriolis force disappeared. This is why you have these features. You know, you also get countercurrents, undercurrents, and so very, very complex circulation. Again, this is just for you to note. And I also show you the other image here is with the temperature transect, a vertical transect showing you the temperature field near the equator in the Atlantic Ocean. And you can derive these current systems from the shape of the temperature lines of the isotherms that you can see here. You know, it's all these shapes that you get are actually the signature of currents. It's to do with the adjustment of the internal density field, which includes the temperature, to actually the forcing, the wind forcing at this. Okay, all right.